Welcome back to the Deep Dive. Today we are unpacking a brand new research paradigm, one that suggests video generation models are much more than just tools for making cool cinematic clips. We're diving deep into what the research calls thinking with video, which, well, it leverages models like Sora 2 for some really sophisticated, genuine multimodal reasoning.
And our mission today is to go straight into the data that's supporting this. We're focusing on the findings from the new Video Thinking Benchmark, or VideoThinkBench. This is really the first systematic analysis that shows how using a dynamic video pipeline actually stacks up against, the traditional methods.
The traditional methods being text-only or image-based reasoning.
Right. We want to know, does giving an AI the ability to visualize a continuous process fundamentally change its capacity to solve problems?
Okay, so let's unpack that. We know the heavy hitters in AI reasoning. We have thinking with text. Things like chain of thought, where a model just writes out its steps.
And thinking with images, where a model might output a diagram.
But those approaches, they hit some pretty solid walls. I mean, if you use an image, you are fundamentally restricted to a single static moment.
That's the key limitation. An image fails completely when you need to represent dynamic processes or continuous changes or the motion of something. You just can't show a ball rolling or a line being extended. Plus, older models tend to keep text and vision as separate processing streams. The core problem has always been a lack of a unified temporal framework, a space where text, vision, and time all merge.
So if thinking with text is like describing how to build a clock, and thinking with images is like drawing a static blueprint, thinking with video, or TFE, is introduced as the mechanism of actually watching the clock being assembled step by step over time.
That's a great analogy. TFC aims to fix this by using video generation to bridge visual and textual reasoning within a single temporal framework. By enabling dynamic visualization, imagination, even drawing. It performs a kind of dynamic reasoning chain. And VideoThinkBench was built precisely to test how well this works.
So jumping right into the benchmark itself, VideoThinkBench is massive. The researchers compiled, 4,149 samples, spanning two core categories, vision-centric tasks and text-centric tasks. It's a very robust test.
It is. And if we focus first on those vision-centric tasks, these are designed to test spatial reasoning and inductive abilities, things that rely on the model visualizing actions like simulating physics or drawing geometrical lines. This category includes four main challenges: eyeballing puzzles, which are pure geometry, mazes, visual puzzles for pattern recognition, and an abstract reasoning set called ARC-AGI-2.
And this is where that video generation capability starts to really shine, especially with the eyeballing puzzles. These tasks demand, precise estimation of geometric properties, things like finding a midpoint or the exact center of a circle.
Or where two rays would intersect. High-precision virtual geometry.
So how did Sora 2 do?
Well, when you evaluate it, the results showed a genuine capability lift, using what they called the major frame evaluation method, and we can talk more about why that specific method is so important in a moment. Sora 2 averaged 40.2% accuracy. That's a notable leap over the leading static vision language models. Claude 4.5 Sonnet scored 35.1%, GPT-5 High was at 29.7%, and Gemini 2.5 Pro at 26.5%.
So you're seeing a 5 to 10 point bump just by adding that dynamic temporal element. That's significant, especially on tasks that need sequential construction. What specific examples showed the greatest strength?
The strength is directly tied to that dynamic visualization. For instance, Sora 2 got a remarkable 88% accuracy on the ray intersection task and 70% on a circle center task. If you think about these problems, they aren't solved in a single flash. They require the model to sort of simulate the geometric construction, extending a ray, reflecting a line, that kind of thing. This ability to mentally draw the work over time is the core advantage.
Which reinforces why the method of evaluation is so critical here. The researchers couldn't just look at the final frame and say, correct or incorrect. They had to introduce this major frame evaluation.
That's right. The major frame evaluation is essentially an aggregation method. It averages the visual signal of correctness across the video's entire duration. You're treating the video output like a noisy signal that you need to smooth out over time to find the real answer. And this method achieved the highest correctness at 40.2%.
Which significantly outperformed just looking at the single last frame.
It did. The last frame evaluation only hit 33.4%, and it certainly beat the audio evaluation, which was only 28% for these vision tasks.
So the findings suggest that the temporal consistency, the fact the model maintains the construction throughout the video, is absolutely crucial. A single snapshot just doesn't capture the fidelity of the reasoning.
That's the takeaway. The system needs the time dimension to show its work. Now, moving beyond geometry, they also looked at inductive reasoning with visual puzzles. These are classic pattern recognition tasks. And here, SORA 2 demonstrated a clear capacity to recognize and apply complex patterns involving color, shape, and size, things like symmetry, gradients, and so on.
It seems highly competent here too, but maybe not as dominant as with the geometry.
Correct. SORA 2 averaged 67% on color-filling tasks, which put it close to Gemini 2.5 Pro's 73.9%. And its 64.9% average on shape drawing tasks was comparable to Claude 4.5 Sonnet's 68.6%. It's in the top tier, but that dynamic advantage isn't quite as pronounced.
And we see a distinct limitation when the complexity shifts a little bit, right?
Yeah.
Based on the maze-solving results.
That's a crucial detail. SORA 2 managed a 40% success rate on traditional standard square mazes, but its success rate dropped to 0% on more complex hexagon and circle mazes.
Wow, to 0.
0. This tells us a lot about the model's training data. Its dynamic reasoning is highly optimized for structures it has likely seen a lot, standard grids. The moment you introduce complex, non-standard geometries, it struggles to adapt. Okay, now let's transition to the text-centric tasks, because this is where the findings become quite surprising and, frankly, counterintuitive. These tasks assess abilities from benchmarks that usually belong exclusively to large language models. We're talking GSM-8K for math, MMMU for general knowledge.
Right, these are problems you'd solve by writing down equations, not by making a video. Yet the results here are genuinely impressive. SORA 2 achieved performance comparable to top VLMs in terms of audio accuracy. You got a staggering 98.9% on GSM-8K. Those are grade school math word problems, and 92% on Math 500. It also did really well on MMMBench, getting 90.1% audio accuracy.
But what's fascinating is the massive gap that opened up between the output modalities. SORA 2's audio accuracy, its final spoken answer, was consistently and significantly higher than its video accuracy, which was its attempt to show the work. For GSM-8K, the audio accuracy was 98.9%, but the visual process shown in the video was only correct 75.7% of the time.
That's a profound disconnect. So the model knew the correct answer well enough to say it, but when it had to visually illustrate this step-by-step reasoning in the video frames, it often failed or was inconsistent.
It creates a fascinating mystery, and we should note, for these tasks, the model was specifically told to provide a written solution within the video frames and only state the final answer in the audio. So that ability to embed coherent text in video is fundamental to the whole concept, but the visual part clearly lagged.
Which leads us right into the analysis.
Yeah.
How does SORA 2 get these impressive, yet sort of disconnected reasoning skills?
Well, they started by confirming its learning style. It operates as a few-shot learner.
The ARC-AGI-2 task is the perfect test for this. It's an abstract pattern transformation challenge. And top VLMs really struggle here, with accuracy usually under 6%. But SORA 2's performance benefited significantly from seeing multiple input-output examples versus just one. That difference in accuracy firmly establishes its reliance on few-shot learning.
And if we connect that back to our earlier discussion, we can draw a parallel to the concept of self-consistency. It's a method used in language models to improve accuracy. And in this context, the major frame evaluation we talked about acts as a form of temporal self-consistency. It's like a powerful denoising filter.
And the data shows just how robust that temporal signal is. On the ArcConnect puzzle, a really difficult task, the single last frame accuracy was only 58%. But the time average major frame accuracy, just smoothing out the noise over one video, boosted that to 68%.
But here's where the scaling really kicks in. When the researchers aggregated the results across 5 independent generation attempts, so asking it to solve the problem 5 different times and taking a majority vote, that final accuracy shot all the way up to 90%.
From 56% to 90%. That's incredible. It shows the model's core intention is highly accurate, even if the visualization in any single frame might be flawed.
Right. But now we have to return to that textual strength. The 98.9% on math problems contrasted with the fact that 43% of the videos showed unreadable or incorrect logic. That demands an explanation. If the model got the answer right but couldn't show its work, where did the right answer come from?
It's the central mystery.
The researchers tried to solve it by manually analyzing the reasoning process. And even when the final answer was correct, that manual analysis revealed that a startling 43.48% of the video processes were unreadable or incorrect. Only a tiny fraction, just under 14%, were deemed completely correct visually.
It really does sound like the video part is the artist trying to draw the steps, but the mathematician who solved the problem is working somewhere else. So what's the hypothesis? Where is this reasoning ability coming from?
The leading hypothesis, which came from experiments with the WAN 2.5 model, suggests mediation. When WAN 2.5's internal prompt rewriter model was turned off, its text-centric reasoning ability almost completely vanished, nearly zero accuracy. This rewriter acts as a preprocessor. It takes the text prompt, solves the math internally with a fast language component, and then feeds the solved problem and final answer to the video part for visualization.
So the strong text-centric reasoning likely comes from an internal preprocessor model, not from the video component solving the math from scratch by drawing out the steps. The video component is essentially illustrating a solution it was handed.
It seems that way. And the researchers ruled out data leakage, confirming these abilities are inherent, even if they are mediated by this structure. It's a key structural finding. The impressive performance on geometry comes from the video generation itself, but the performance on math appears to be leveraged from an internal text processor.
Okay, let's bring the key threads together. The video generation model, SORA 2, demonstrated really powerful spatial reasoning and inductive abilities, specifically excelling at tasks that need geometric simulation. This, combined with its surprisingly competitive though mediated performance on text-centric tasks, strongly positions thinking with video as a potentially unified multimodal reasoning paradigm for the future.
To recap the primary takeaways for you. First, SORA 2 excels at dynamic geometric tasks like ray intersection, which confirms the value of that temporal dimension. Second, the major frame evaluation proves that the full video provides a much more robust signal for accuracy than just single static frames. And finally, the high textual performance seems strongly tied to an underlying prompt rewriting mechanism that solves the problem before the video component tries to visualize it.
And that reliance on an opaque internal mechanism for accuracy brings us back to our central point. SORA 2 struggled to clearly write out its reasoning process in the video, with over 43% of the visual steps being judged as unreadable or incorrect, even while the audio provided the correct final answer. This raises an important question for you to consider. Does successful reasoning always need to be linear and visibly demonstrated through steps we can follow? Or is this answer-first approach, mediated by hidden preprocessors, a valid form of abstract intelligence, even if it remains visually opaque?